So welcome again, and thank you for joining us first thing in your morning. For those of you who haven't joined us for the last few sessions, my name is Jenna, and I work with the Community Energy Association, or CEA. So I'd just like to quickly introduce you to CEA and the Kootenay Clean Energy Transition Project. So CEA is a BC-based nonprofit. We've been working for over 25 years with local government and Indigenous communities across the province to reduce emissions, conserve energy, and help progress us to a low carbon and healthy future. Next slide there, please, Rob. Perfect. So the Kootenay Clean Energy Transition, or KCET, is a project that was developed to address shifts happening in the energy efficiency, renewable energy, and home comfort space. So through KCET, we want to help Kootenay and boundary communities prepare for a more energy efficient and healthy future through capacity building for the building industry, community workshops to help increase knowledge and awareness, and pilot projects that we can test and scale up. So thanks to the generous support of the organizations you see listed at the bottom of the screen there, we're offering this free webinar as a part of that training and capacity building. And then just the next slide there, please, Rob. Perfect. So I'd like to begin our session today by acknowledging the Indigenous peoples from all of the diverse and beautiful places that we're joining from. So the land on which I'm currently joining you from is now known as Nelson, but for thousands of years was occupied by Indigenous populations and is the traditional territories of the Snaiks Nation, the Silks Nation, and the Ktunaxa Nation, and is home to the Métis and many diverse Indigenous persons. So I just like to acknowledge with gratitude and respect that the joy I am privileged to experience daily in these mountains and waters is in thanks to their generations of stewardship. All right, so just quickly, I'll go over a couple of housekeeping items. As we go through, we do encourage you to raise your hands if you have any questions, and Rob will be happy to answer those questions right away. If you prefer to put them in the chat, we'll just save all the questions in the chat for the end and go through them at that point. As you would have noticed when you logged in, we are recording this session. So this will be sent to everyone here via email later on this week, and we'll also post it on our website. So if you'd like to go back to the recording, it will be available for you there. For those of you collecting CPD points through BC Housing, I'll send a confirmation email following this session, just confirming your attendance. And that's that. So it's with great pleasure that I introduce again Rob Pope, a senior consultant with Ecolighten Energy Solutions. You're all probably pretty familiar with Rob now, but he has vast knowledge and experience in the HVAC industry. He's been involved with installing and servicing energy efficient systems since the get-go. So a huge thanks to Rob for joining us today and sharing your wealth of knowledge with us, and I'll pass it along to you.
Thanks, Jenna. Hi, everyone. Thanks for attending this morning. We're going to talk about hybrid systems. Let's just go through the agenda here. We'll start with what is a hybrid system, the definition, difference between gas, auxiliary versus all electric systems, the standard technologies that are involved in hybrid systems, and the new and emerging technologies. And then we'll talk about hybrid applications and processes. For example, typical hybrid options, using balance point to select equipment, and I can't emphasize how important that is. So we're going to spend a bit of time on that, and the general challenges and considerations with hybrid systems. So let's get started. So what is a hybrid system? The difference is, and it gets confusing for some, if you have a heat pump in all electric system, you'll have a fan coil probably. You may have electric auxiliary heat built into that fan coil. Whereas with a hybrid system, you'll have, as you can see on the left there, you'll either be a forced air gas furnace or forced air or a gas boiler, but you'll still have the heat pump. Either way, the hybrid system, and just like in all electric, your auxiliary heat in hybrid systems, it'll be gas, will take over when the heat pump's capacity can't keep up with the load. Main differences: primary heat is a heat pump in both cases with all electric and a dual fuel or hybrid. Secondary heat with all electric, as I suggested, is electric, whereas with a hybrid, it's gas. Upfront costs and operational costs can be higher with an all-electric system compared to gas, but that depends. It depends on the choice of the heat pump and how much of the time the auxiliary heat needs to be on. And we'll go into a little more detail about that later on. GHG emissions, well, of course, you know, it's no contest. All electric is minimal. There's some, but it's minimal. And with a hybrid system, gas, a fossil fuel being your auxiliary heat, of course, there's more GHG emissions. Other considerations between the two is the all electric requires more electrical panel capacity. With a hybrid system, when the capacity of the heat pump is no longer able to keep up, basically the gas furnace or boiler will say, okay, I'll take over from here, and does the whole job. Whereas with a all electric, and if it's managed correctly with the right equipment, sometimes it'll blend the electric and the heat pump together. The technologies, basically forced air or hydronic, you know, radiant or forced air systems. And in the forced air case, your primary heating is going to be an air to air heat pump. It can be ducted or ductless. And the backup or auxiliary heat will be a coil built right into the furnace, for example, or electric baseboards. Primary heat with a hybrid system is still a heat pump. But the secondary will be a gas furnace. With a hydronic system where you have radiant heat, like in floor, or radiators, it's an air to water heat pump. That's the primary. And with an air to water system, you can have your backup as electric with a separate independent boiler, piped in series or in parallel. You can have an electric element in the booster, or sorry, as a booster in the buffer tank, or you can have electric baseboards. There's a number of options. Likewise with the forced air, your primary heat is still a heat pump, and your secondary heat is going to probably, in this case, be a boiler, gas boiler for your auxiliary and backup heat. By the way, don't hesitate to interrupt me as we go if you have questions or comments. Hybrid systems cost benefits over electrical systems. Capital costs and retrofits, especially if the existing system can be used, is quite a lot less. Operating costs, again, it depends. It depends on the choice of the equipment, the choice of the technology you're using for the heat pump, and the amount of backup time that your auxiliary heat needs to be on. If you have to upgrade your panel to accommodate an all-electric system, it's fine if the panel has the capacity, but if it doesn't, then obviously your upfront costs are going to go up quite substantially to accommodate an all-electric system. So when in that case, when compared to a hybrid system, the upfront cost of electric is substantially more. There's also less disruption. If you can take the existing system, you got a forced air gas furnace, it's reasonably new, well maintained, you know, and you just add a heat pump to it. You put a coil in the plenum and an outdoor unit outside and connect them with refrigerant and wiring and so forth. It's an awful lot less disruption. Technology. So I've been around long enough to remember when the first heat pump came out in the late 70s, and I happened to be an apprentice then, and we installed one. It was a single stage, big, awkward unit. It is a technology that has stayed with us. They're still around. You can still get these single stage units, but they've been surpassed by other technologies, for example, a two-stage. So as you can imagine, a single stage is either on or off, right? And you can see those high curves, you know, it can overshoot the set point quite a bit. So then the two-stage heat pumps came out and we all thought, oh, hey, this makes tons of sense. We got it sorted now, because most of the season right across this country is shoulder season, and you don't need the full capacity all the time. So having that staged heat pump made an awful lot of sense. Then came along variable refrigerant flows. So in the previous example, single stage or two stage, they're either on or off. Granted, with the two stage, the first stage is lower, but it's still on or off, on or off, on or off. Whereas with a variable refrigerant flow, that compressor is ramping up to meet the load condition. It sneaks up on the load. It's not full on and then all off. It varies with the load condition. So as you can imagine, it's a lot more efficient, up to 40–50% more efficient than single or two stage. And one of the other benefits of it is you can actually have one outdoor unit doing multiple indoor units. And it's a lot quieter. It's more expensive though. We thought we had the pretty good technology with those variable refrigerant flows, and then came recently, fairly recently, cold climate heat pumps. Cold climate heat pumps solved a lot of problems, especially in Canada, where most of our country is in cold climate zones. And the problem used to be all the time is, if you were in you know, somewhere in the interior or most of this country, you'd say, why would I get a heat pump that can only serve me until just around 0 degrees Celsius or just above? And then the rest of the time I need my backup. It doesn't make sense, right? But now we have a technology, cold climate heat pump, that can actually meet a load condition quite effectively. I mean efficiently, down to sub-zero temperatures. We've seen them go down to as low as -30 and still operate well. You can see on this graph here, that red line represents what we call a performance curve, right? On the right-hand side of that graph, we're starting at 47 degrees Fahrenheit. That is the starting point for the measurement capacity of all heat pumps. So if you have a 4-ton heat pump, that's at 47 degrees Fahrenheit. 5-ton heat pump, that's at 47 degrees Fahrenheit. That's the starting point for all the nominal capacities. But as most of you probably know, when the temperature starts to drop outside, so does the capacity of the heat pump. Also, correspondingly, in most cases, so does the efficiency of the heat pump. They both drop off. And you can see standard heat pump here in blue, the 2-stage or single stage, it doesn't matter. By the time you get to just a little bit below freezing, just a little bit below 0 Celsius, so you know it's got nothing left. We can't do anything for you. If you get the variable refrigerant flow heat pumps, they're better technology. They do much better. It's a shallower curve, but nonetheless, it still drops off by the time you get to minus or say 10 degrees Fahrenheit, especially to 0 Fahrenheit. You really don't have enough capacity to do the job. So what started as, say, a 5-ton heat pump now only has 1 ton left of capacity. On the other hand, that cold climate heat pump, it's a straight line. You can see for quite a long ways down to 5 degrees, which I think is about -15 Celsius. Forgive the Celsius Fahrenheit stuff. I'm an old timer, so I'm still more comfortable with the Fahrenheit. But anyways, you can see that at 5 degrees Fahrenheit, which is I think minus 15 Celsius, we're still at 100% capacity and close to 100% efficiency. And then when it does drop off, it drops off slightly. This new technology is kind of revolutionary. We have developing technologies, pretty new. It's been around in commercial industry for a while now, but for residential, the gas heat pump is still relatively new. Fortis BC is working on pilots with a couple of gas heat pumps, Thermalift and the other one, Rover. And those pilots are coming along pretty good. So there's some advancement in that technology that we'll probably see on the market pretty soon. Then there's a combined heat and power technology. That's still really new. And I won't go into that in too much detail because it's not, it's not around the corner. You can't see it down the road. And to be honest with you, I don't know too much about it. Typical hybrid applications. The most common one, and we've been doing this forever. You can imagine in a lot of parts of this country, the Okanagan, for example, in Southern Ontario, Southern Quebec, air conditioning has always been a strong demand. And so back in the day when I was apprenticing in the early days back then, I mean, that was half your business was installing air conditioners. Well, that is a hybrid system because an air conditioner, think about it, is a heat pump. It's just, instead of extracting heat from one source and dumping it to another, in the case of an air conditioner, it extracts the heat from the home, dumps it outside. A heat pump does it both directions, right? Air conditioner is a heat pump, but just a one directional heat pump. And we retrofitted air conditioners onto existing gas furnaces forever. So it's a pretty standard approach and practice for putting heat pumps, for example, instead of air conditioners, onto existing systems, or replacing the existing system. If it's an old furnace, for example, you don't want to keep it. It doesn't make sense to put something new on something that's falling apart. You would have a new furnace and a new heat pump, ideally matching brands, matching models that talk to each other. Benefits in the case of a retrofit where you can use the existing furnaces is pretty self-evident. You don't have to replace that furnace. You just add on a heat pump. You're going to save on the upfront cost quite a bit. Either way, when you put a heat pump on a forced air system, you're going to get heat. Most of the time, if you choose newer technology, variable refrigerant flow, or especially cold climate, and you're going to get cooling in the summer. One of the challenges, of course, is if the existing ductwork can handle the capacity of the heat pump. A furnace is a lot more forgiving than a heat pump is. If the ducting is undersized, you probably have to do something to remediate that. You have to find a way to reduce the pressure that may cause the coil of a heat pump to freeze up. So it's pretty critical that the ducting is sized for the heat pump and not just for the furnace. Touch briefly on this air to water system. You see you're replacing a boiler, for example, in an existing home. It's pretty straightforward if the home has relatively modern, maybe over the last 30 years or so, type of radiant system, inflow radiant in a topping coat or underfloor even. And all you're doing is taking out that old boiler and you're putting in an air to water heat pump, and with a few controls, pumps and valve changes, you're tapping into that existing delivery system, which is the radiant piping running through the house. That's good. What it doesn't do in that case is give you air conditioning. And air conditioning is part of the plan, then you have to do that a little differently. We'll talk about that in the next slide. Here's where we see some of the issues. So in a lot of old houses with radiant heat, there might be radiators. Radiators traditionally, in more than 90% of the cases, heat the home with high temperature fluid running through it. Heat pumps don't deliver high temperature water. The degree of temperature for your typical radiator is somewhere, between 160 and 180 degrees being delivered to that radiator, whereas a heat pump, it maxes out around 130, and that is like having your gas pedal to the max. You don't want it to be there. You would rather be 120 degrees or less. And so what that creates is an issue of tapping into the existing system with a lower temperature and being able to meet the heat demand. This is why load calculations and other things are important. But if it can't meet the heat demand, then you may have to supplement it with a bit of forced air. Now, in this case, it doesn't have to be, you don't have to put in ducting, retrofit ducting into a house that never had it before. You can always just put in ductless splits, attach that same outdoor unit. So this is what we'd call a combo system. So as I said before, I can't emphasize the critical importance of balance points. It's kind of like load calculations. If you don't know your loads, and similarly, if you don't know your balance points, you're just guessing. So as we talked about, and you all probably know, in the winter, it's heat extracted from the outside air, transferred to refrigerant, and delivered as heat inside the space. Of course, as the outdoor temperature drops, there's less of that heat. In a lot of climate zones, and depending on the load of the building, even with a cold climate heat pump, it's very likely that you need to have some auxiliary heat for the coldest parts of the winter. But when do you need it? That's what we use the balance point for. Now, there's two types of balance point. One is the capacity. When is that heat pump you're thinking about going to have to hand over the job of heating the home to your auxiliary heat, to your gas furnace, for example, right? That's the capacity balance point. And then there's the economic balance point, which is about efficiency. It's a lot more complex, but it's essentially about when is it economically feasible, not when. It might not be precisely when the capacity gives up. It might be at a different point where the cost of the energy that you're using for backup becomes more feasible or better off to change now instead of later to that backup heat. It's an economic balance point, and we'll talk about that in a little more detail later on. So there's two types of balance points. In either type of system, whether it's all electric or hybrid, you need to find the balance point because you need to know when that auxiliary is going to take over, and then you can see what kind of equipment it's going to need. You can then optimize the system. You can say this heat pump will do better at that balance, has a better balance point than this one over here, and based on the cost difference between the two, maybe I'll go for the better one, or maybe my budget won't allow it. I'll go with a less of a balance or earlier balance point. It helps you decide the cost benefit of the choices that you're considering. And we can see here a whole bunch of different major brands. Here's the Mitsubishi, the Carrier, Armstrong, Daikin, and I could put a dozen more slides like this up there. for the same size equipment, all of these brands and models within the brands all have different performance curves, therefore different balance points. So if you don't do your calculation about where that balance point is, you're just guessing. You need to know they're all different. There's no such thing as a standard balance point. It's pretty straightforward how to achieve your balance point. First, you do your load calculations. Once you've done your load calculations, you select the heat pump technology you want to use. That could be based on a lot of things, among them budget, performance. Either way, you choose the technology you want. And then within that technology, you look for different brands, and then that's when you do the cost benefit thing. Which is going to serve me best? You find the performance specs of the equipment, those performance curves I showed you earlier. You plot that curve on a graph, and then you find the heat loss line, and where that heat loss line, you can see here on the chart, the graph on the left, that heat loss line is a blue line. The heat pump curve is the red line. Where they intersect, that is the balance point. That's the point at which the capacity of the equipment is no longer able to manage the load. Critical among that. In fact, it's required by code. It's just not known and not enforced in most jurisdictions, but it will be, is the load calculations. If you don't know the load, you can't do the balance point, because that's the first thing you need to plot on that graph is, the heat loss. You need the heat loss line to do the balance point. And if you don't have the load calculations, you can't do the balance point calculations. And if you don't do either of those, again, if the system works, that would be a coincidence. And you don't want to depend on coincidence. So the importance of balance points, just to recap, is equipment selection. Selecting the most appropriate equipment based on performance cannot be done without knowing the balance point. Another thing that's important is the electrical panel. Where electric auxiliary is considered, calculating the balance point is the only way to discover the size of the service required on the panel. And this will tell you sometimes, in some cases, where you might have wanted to go all electric, that you might be better off going hybrid, right? Doing the calculation will inform you for making that decision. It helps you do the cost benefit analysis. Obviously, if you have a piece of equipment that can last deep into sub-zero temperatures, you don't need a lot of auxiliary heat. Works at a good efficiency. From an operating cost point of view, it's pretty good. But then you need to balance that with the upfront cost. Is it worth it? It might be, but you don't know until you've done the calculations. And system optimization. If that heat pump is at a good efficiency, it's doing the job, you don't want it to stop working too early in the winter and have a dependency on the auxiliary or the backup for the rest of the time if it's not going to benefit you, right? So optimizing the system, both for comfort and economics, is another reason why balance points are important. So which one to go for? We hear an awful lot about the economic balance point. The fact is the economic balance point is a lot more complicated to calculate. You still have to do the capacity calculation, then you have to add to it. Now have to know the efficiency of the equipment, all the equipment, your gas and your heat pump. You have to know the cost of the fuel, cost of gas versus the cost of electricity using a heat pump at its efficiency. And you have to know, how much time am I going to be in the auxiliary mode? You know, what's the amount of usage between one or the other, the primary heat pump or the auxiliary, your gas. So it's not an easy calculation, and there's no standard number to it. You have to actually do the math. To create an understanding of how it looks, because there's a lot of myths out there about the relative cost of gas to operate versus a heat pump. So this is an actual house that we've done an awful lot of valuation of, and put it in many different scenarios, and used it for NRCan and CHBA to do some modeling and a bunch of other things. So just think about this house. This is in Vancouver, -7 degrees Celsius, 19.4 degrees Fahrenheit is its climate condition. That's a winter condition. And what we did was we took this house and considered 3 things. The house as is, the house with a light retrofit. That means changing the heating equipment, changing the windows, and maybe putting some insulation in the attic. So light retrofit to the house, sealing it up a little bit, making it less drafty. And then a deep retrofit, that's, gutting the walls, putting insulation, insulating, improving the insulation in the whole envelope, keeping it, and triple pane windows and attic insulation and so on, and making it even more airtight. And for each hour that this building is heating during design conditions in the winter, this is what it costs. Now look at the 1 hour cost of natural gas furnace. In this case, as is $1.24. 1 hour of electricity, say there was no gas furnaces, it was just electric baseboards, straight electricity, $2.17, almost double. If you take your average heat pump, a standard heat pump, decent quality, but not the best, you should get a COP of 2.0. All that means is it's 200% efficient. 1 kilowatt of electricity buys you 2 kilowatts of heat, right? And at 2.0 COP efficiency, again, very standard, it's already less than the cost of gas for that same hour of heat. If we go to the higher quality heat pumps, the variable refrigerant flows, the top models of most brands, we're at least at 2.5, 250% efficiency. And now we're at 87 cents for that same hour of heat. And on it goes. So you can see the scale of difference. If we go to the highest efficiency, like the top tier cold climate heat pumps, or the a geothermal, for example, you're down at 72 cents for that same hour. And obviously, as you retrofit that building, and I should emphasize that I think the industry consensus is, whatever you do, if you can, envelope first. If you can fix the building, then you need less of a system, a mechanical system for it. So envelope first, as you can see here, has huge benefits if the cost of that energy upgrade is in the budget. So just to recap this, with a condensing high efficient gas boiler or furnace, 95%, that hour of electricity costs you $1.24. The cost of that hour of heat, just using straight electricity, like baseboards, for example, is $2.17. If you have a heat pump with a coefficient of performance of 1.75, which is, an off-the-shelf heat pump, really, that's all you need to have to match the cost of gas for that same hour. in the example that we just showed you, or I just showed you here, as I said, a COP of 1.75. It is below the demand, and it will be the economic balance point. In other words, is the largest heat pump that can manage the load. So the more capacity that heat pump can do, the better off you are economically. The less backup or auxiliary, the better off you are. So instead of trying to do a whole pile of complicated calculations, a good default is find a heat pump that you can afford that has the biggest capacity to manage the load, giving you the least amount of auxiliary or natural gas required. So recap, understanding the balance point of heat pumps is critical for choosing what technology to use, brand, equipment, and even the models within the brands. Choosing which type of auxiliary system, for example, balance point, when you were thinking about all electric, might show you, hey, you know what, maybe it makes more sense to go with a hybrid system. Knowing what to expect from an operating cost perspective and optimizing the system performance. These are all good reasons for doing the balance point calculations. It begins with load calculation. That is critical in all retrofits, all new construction, all mechanical systems of any type. Load calculations first, really critical. Some of the challenging considerations of hybrid systems relate to the policies from federal, provincial, and even some municipal governments to address climate change. And as such, here in BC, we have the STEP code. Just recently, throughout the province, there's a minimum required STEP code 3 in all jurisdictions with authority have to comply. And as you move up the STEP code ladder to 4, especially to 5, it becomes increasingly difficult to model in a gas appliance and still meet the metrics of the STEP code. Because of the efficiency of gas being less than 100%, it penalizes the numbers that your modeling puts out to a degree that it may affect the ability to reach step 5. You can do it, and it's been done many times. It just means if you intend to have a gas boiler or a gas furnace in the house, you probably have to really amplify the thermal efficiencies of your walls, of your glazing, the air tightness of the building. You have to compensate for that elsewhere. It's doable, but it's harder. One of the most common problems in retrofits is the existing ductwork. The existing ductwork tended to be undersized. So that's why most people's experience with forced air systems is, it's noisy, right? The undersized ducting, that's what it does. It creates noise and other things. It's not ideal with a forced air furnace, gas furnace, but it can still work. But as soon as you stick a refrigerant coil in that system, now your range of tolerability has shrunk, because that refrigerant has to do, that's to change states. There's a very small window of tolerance for airflow across that coil. And so it's important that when the existing system is taking a heat pump, that the duct size is checked to make sure it's adequate to deliver the flow across that coil that's going to let it operate, function properly. And the only way you can do that is to do a pressure test on the system. But either way, that is the issue. Now, the good news is there's a lot of ways to deal with that. Any good mechanical contractor, HVAC contractor can figure out ways to relieve some of that pressure, add a run here, add a return there, create a bypass. There's ways to do it. As long as it's addressed, then that's the important thing. The biggest thing from my perspective, and a lot of people in the industry, I guess, is the standards of practice. We don't have any. We just don't for HVAC. There's little bits and pieces here and there in different parts of the code, section 936 and section 932. There's a lot of standards of practices that you can retrieve from ASHRAE, which is more for commercial buildings. And there are standards of practice from industry organizations like TECA or HRAI, but there's no consolidated set of standards of practices that you can follow, that an authority with jurisdiction will verify that you did. Just like you do plumbing, and plumbing inspector shows up, gas inspector shows up, electrical inspector shows up. No such thing with HVAC. That's probably the biggest issue, and it creates a large vulnerability for homeowners. That is changing. Standards of practice for HVAC is coming. It's in development, and it's moving along at a pace that feels like it's going to show up in the market, in the industry soon. So that's probably one of the biggest challenges. Is it's similar to how the cliche is, if you come across a reliable auto mechanic, that's gold, right? Because there's this tendency you just don't trust them, right? It's probably an unfair characterization of that trade, but it's the same with HVAC. There's a lot of good HVAC contractors out there, but there's also a lot of unqualified contractors, and that's probably one of the biggest challenges in our industry right now for residential. There's a few resources here. I think that this is going out to everybody. Is that right, Jenna? Yeah. These are really useful resources. Anything you want to know, you can click on any of these and you'll get wealth of information. And that's it.
Great. Thank you, Rob. That was wonderful. We have some time now for questions or comments or just a general discussion with Rob. We've been pretty quiet in the chat. Gregory had just a comment there that his neighbor had a cold climate heat pump installed at Wassa, which is near Cranbrook, and it runs down to -15 Celsius before it uses the backup electric coils. And then he also added in the clarification that -4 degrees Fahrenheit is -20 degrees Celsius for anyone who doesn't have Rob's Fahrenheit brain. Oh, perfect. Thanks, Rod. So Rod just put a question in the chat asking, how common is it for residential HVAC contractors to provide load and balance point calculations, particularly in retrofit situations?
It's very uncommon, unfortunately. Very uncommon. It's a recent requirement in the industry, really, because in recent, I'm thinking like for somebody who's been around for quite a long time. For say 10 years ago, maybe a little more than 10 years ago, people were retrofitting gas furnaces with new gas furnaces and maybe putting air conditioners on there, right? But with climate action plans of governments, with the new changing technologies, the cost of energy, the demand from homeowners, there's a lot of incentives and rebates. There's a lot of reasons why these new processes are emerging now that require more diligence and more professionalism. And so there's a lag in the industry. I mean, it's not unusual at different times in the industry that I witnessed when changes came. There's always a lag, the industry catching up. And that's the issue right now. It's there's contractors that do all that and do it well, right? But they're not many. I'd say it's an exception right now, but it's an exception that has to change. It has to become the normal. And it's going to happen whether it happens voluntarily, the industry just adapts and everybody just does it, or it's regulated. You have to do it. You can't get a permit unless you do it. It'll be inspected and won't pass unless you do it. That regulatory verification, enforcement, and so on of that kind of practice is coming, right? And the question is whether the industry will adapt to be ready for it, or they'll try and catch up when it happens. It could go either way, but I'm encouraged by a lot of HVAC contractors and industry associations and various governments and private organizations all pushing to develop the tools and support necessary for contractors to adapt to the changes that are coming and voluntarily do things like load calculations and balance point. That's happening a little bit more, and a little bit more, a little bit more, but right now it's still an exception.
Yeah, great, thank you. Darren asks, can you provide DHW?
Domestic hot water with a heat pump? Is that the question?
I think so. Darren,
or does he want me to give him a domestic hot water system? What exactly is the question? Sorry.
He says yes. So can you provide domestic hot water with a heat
pump? You can with some heat pumps, air to water heat pumps. They have to be air to water heat pumps. Some of them will have the ability to have a high temperature to deliver water to your storage tank, for example, at a temperature that's acceptable to avoid legionnaires and that kind of stuff, right? You don't want that water temperature in a tank to sit at too low of a temperature, because it creates bacteria and stuff like that. So it has to be a certain temperature to avoid that. There's a few heat pumps on the market that'll do that. And then there are the ones that will preheat the domestic hot water. It won't give you the delivery temperature, the standby temperature you need, but it'll get you really close, and all you got to do is boost it. And that's actually the ideal way to deal with domestic hot water with an air to water heat pump, is preheat it, and then the energy you need to top it up, whether it's, if it's electricity, for example, because that's the simplest way to do it. It doesn't take much energy.
And then that requires 2 tanks, he asks.
Well, you have your domestic hot water tank, and if you're putting an air to water heat pump, you need a buffer tank. So if in air to water, you're going to always need a buffer tank. Don't let anybody tell you don't. You have to have a buffer tank. And so that's where your preheated water lives and gets delivered to your domestic, right? And yeah, it's also the most likely place you're going to put your backup heat. You're going to put electric elements in that buffer tank.
Great. Oh, Darren says thanks. Ken asks, if you size a heat pump for the heating load, isn't it going to be oversized for the cooling load?
I don't know. Depends. There's sometimes the cooling load is the dominant load in the more high performing homes, right? If it's an existing old drafty home in the shade, then maybe, and it's not in the part of the country where you're getting, routinely temperatures in the high 30s or mid 30s, then yeah, maybe Who knows? You need to do a load calculation to figure that out. But it does happen. It's an unbalanced load. It can happen the other way. Your cooling load can be double your heating load, or your heating load can be double your cooling load. It depends on a lot of things: exposure, glazing, location, and all kinds of stuff, right? Ideally, because you bring up a good point, your loads are balanced. You have the same heating load as cooling load. That's the ideal situation, but you don't get that luxury all the time. Either way, you can deal with it. There's ways to deal with it. If your dominant load is heating and it's, say, double the amount load you need for cooling, you know, you just, or vice versa, you can deal with it effectively if you're an HVAC contractor that knows what they're doing.
Great, thank you. Yeah, Gregory, good point. He just has a comment here that saying when selling heat pumps in Cranbrook, the natural gas is cheap enough that it is cheaper than heating with a heat pump. But what makes the sale is the air conditioner. So yeah, having consumers kind of.
Yeah, but that is a kind of a, I would challenge that statement. Heating with gas is cheaper than heating with a heat pump. Are you sure? Like, what kind of heat pump? Which heat pump? What technology are you talking about? Right? You know, it's not necessarily the case, right?
Can I respond to that?
Sure. Yeah, please. Yeah.
The price of natural gas is predicated from the distance from Fort Nelson, BC. The price of natural gas in Cranbrook is on a huge gas line that delivers natural gas to California. The price of natural gas in Cranbrook is way cheaper than the price of natural gas in the Lower Mainland. So even with 300% efficiency, the price to heat with gas is still cheaper than the heat pump at the high efficiency. So, but gas is cheap right now. Gas might go up in price, and I'll give you that.
That's a very specific, yeah. So it's a regional thing. So where you are, it's higher, right?
Yeah.
Or sorry, gas is cheaper. How much is it per gigajoule?
It's per gigajoule, $6.
Is that all in, carbon tax, everything?
Well, all in, I'll maybe say 9.
9, okay.
Yeah. So, and I can send you something for that, but yes,
that would be great. Yeah, I mean, if you wouldn't mind doing trouble, and I appreciate that clarification, because it's also this different situation in parts of northern BC as well. And if you go across the country, it's it's like all over the place. So it is important to do that. Well, this is the whole reason. Like, you wouldn't know that unless you did the calculation, right?
Yeah.
And that's the whole point, is do the calculation, right? And this is what you learn. Right? These are the things you discover.
Yeah. But basically, the other thing, of course, that makes the sale is the carbon, etc. And if the person is motivated by that, then they're pretty happy with it. But Cranbrook had 40 degrees C last year, and most people are begging to get air conditioning now. So, yeah. Yeah.
As soon as air conditioning becomes something that's, you're thinking about, then, I mean, I would never even consider talking somebody into getting an air conditioner. Might as well be a heat pump, right? Because the heat pump does that. You might as well, right? For the difference in cost, you might as well have a heat pump.
Well, the one last thing, of course, is the elephant in the room is the person's just fine with their natural gas furnace. And a heat pump is about maybe $15,000. And you're going, what is the benefit to this? And I cannot tell them that they're going to save money by going to the heat pump at the present conditions. The natural gas is just too cheap. And maybe down the road, the price might go up, but not right now. So then the other thing you mentioned is, oh, by the way, do you know you get air conditioning with this? And then they are on board. Yeah.
Yeah. And potential rebates, incentives as well, right?
Yep. Yeah, but the $5,000 rebate is there for sure. And but when you work out the numbers, one thing our presentation didn't have here is a spreadsheet showing the capital cost of the heat pump and what it has to do for you to get the money back, right? So what's the payout? But that's regional too. So I get it. It's
Oh yeah, I mean, it depends. I mean, wherever you go in this province, it changes dramatically what the margins are, availability, like contractors, how competitive. You
Yeah.
might have one contractor serving a large region and, you know, they got the market cornered.
Yeah.
Their margins are really high. Or you have, you know, just limited accessibility to product range because of location of suppliers. You know, in the East Kootenays, you know, most of the contractors I've talked to there, you know, they get all their product from Calgary. And the way of doing things is kind of Calgary centric, right? You know, this is, people put in electric furnaces with heat pumps for some reason. You know, it's, you know, obviously when you sit and think about it, you know, you change, but that's pretty standard stuff, right? So it's very regional, like you said.
Yes. Oh, one more thing I'll mention. I don't know how many people here are from the watching here from the Columbia Valley, but the Columbia Valley runs from Cranbrook up north to as far north as Golden, and most of these properties do not have natural gas. It reaches as far as a little town called Skookumchuck, where there's a large pulp mill, and that's where it ends. And the BC government has no intention of running that natural gas line further north. That's it. I mean, with carbon issues and all that, that's it for natural gas. So all those communities are serviced by propane. Now that's where the heat pumps blow the doors off them.
Oh yeah, same like you know, I grew up on an island, or not. I didn't grow up on it. I brought my kids up on an island. There's no, you know, and I spent an awful lot of time talking people into heat pumps because it made so much sense. Because they're, you know, propane deliveries and, you know, the
price
cost
of
of
propane.
propane, and then the worst is diesel. You
Oh
know,
yeah, oh my God.
archaic technology. I can't tell you how many times I've been in people's crawl spaces with dirty, ugly, finicky oil furnaces.
Yes. The price of propane in this valley is $30 a gigajoule.
Okay, so it's a no-brainer then when you don't have natural gas at a
yeah. Thank you very much, Rob. I'll just click off now. Thank you.
Thank you.
Great. Thanks so much for that regional perspective there, Greg. And that's perfect timing. That brings us to 9 o'clock.